In this video, we're going to look at arbitrary families of sets. So what are these arbitrary families of sets? So we say we denote sets by uppercase letters such as X, A, and these can be just a single set. But when it comes to an arbitrary family of sets, there are a number of sets which we might not know how many they are. So they are a group of sets, a number of them. So when it comes to these arbitrary family of sets, we can still perform the set operations on them, that is the union of the set and also the intersection of the set. So now, what is the union of a family of sets? So when it comes to the union of these families of sets, we define them to say that the union of the index family of sets, so the arbitrary set itself saying A, then I there, such that we have I, a member of the indexing set. So I is just an indexing set. So an indexing set is more of a set that is under consideration. So it can be maybe the set of natural numbers, it can be a set of real numbers. So that's the indexing set, and this is denoted as union, where we set I, a member of the indexing set, whatever indexing set it can be, then the arbitrary sets. So you are uniting, or you're bringing together all these sets. We might not know how many they are quite numbers. So A, such that A is a member of some A naught, AI naught, like this, for some I naught, a member of the indexing set. So this is how we define the union of family of sets. So in general, this would mean if we have a set x1 union x2, and you continue doing the union up to, I don't know, xn, like that. So they continue to go, and this is written in general as union up to n. If you're going up to n there, starting from I equal to 1, then xi, like that. So this is what we mean when we talk of the union of the family of sets. So we can also define in the like manner the intersection of the family of sets. So when it comes to the intersection of the family of sets, it's defined as, so you have your arbitrary sets like that. That's that I is a member of the indexing set. Then you're saying the intersection is defined as, or denoted as, I, a member of the indexing set of the arbitrary sets, arbitrary family of sets like that, such that you have A, such that A is a member of A, I, like that. For O I, a member of the indexing set. So this is how we define the intersection of the families of sets. So this is how it must be written, and this is how the set is defined itself. So we'll go straight into looking at a question. So we have this question. It says consider the collection of sets A such that AI is equal to, so it's equal to that, which is 1 over negative I, comma 1 over I. So we're given that interval, that's how the set is defined, such that I is a member of the natural numbers. So the indexing set here is the set of natural numbers. Then the union of the set, the union of the family of sets is, so here we need to find the union of the family of sets. So in order to find the union of this family of sets, what we do is, so we can observe that for every, so we're starting from, so this is I, a member of the natural numbers, and natural numbers begin from 1. So now if we say we have A 1, and we replace 1 where I is, we have that in the first case we have 1 over 1, so 1 over negative 1, like that. Then this will just be comma 1 over 1, and this gives us negative 1 comma 1. So this is the first one we get. Then if we get second one, we have that, we have 1, So here it's 2, so replace 2 where that is, and this is negative, so we get negative half, and then we have 1 over 2 like that. Then we can continue to go like up to 3. If we get 1 over 3 comma 1 over 3 like that, so this continues to go, and we can observe from just these three sets that the interval is becoming smaller and smaller and smaller as we approach infinity. So now the union of these sets, is going to be I, a member of natural numbers, that's our indexing set, then the arbitrary family of sets. In this case, we say A1 union A2 union A3. So this goes up to, I don't know, union whatever is going to be what to be there. So these sets continue to go up to what, up to infinity like that. So now if we write these sets, negative 1 comma 1 union negative half like that, comma 2 union negative 1 over 3 over 1 over 3 like that, union, and this continue to go up to infinity, we see that this set here is what is smaller than this one here. So negative half comma 1, this here, this interval is contained in the first one, and also this one here is contained in the first one and also in the one before it, which is negative 1 over 2 comma 1 over 2 like that. So now if we do the union here, we need to have an interval or a set that will contain all of these, and we see that even as we continue to go, negative 1 comma 1 will contain every one of these sets which we will have, because as we approach infinity, the set becomes the interval becomes smaller and smaller and smaller. So we see that this one, the one which we have at first, negative 1 comma 1, will contain all the sets. So the union of the family of sets here is just that I, a member of the natural numbers of I, A is equal to negative 1 comma 1 like that. So this is our union. Now we move on to the next one. So this one is in terms of intersection. It's the same question, but now we're talking of intersection. So if we continue with the same, we know that A1 is equal to negative 1 comma 1, and then we have A2 to be negative half comma half, and then we have A3 to be 1 over 3, negative 1 over 3, 1 over 3 like that, and this continues up to infinity like that. So now we can say the intersection of these sets, such that I is a member of the natural numbers I like that, AI is going to be, so when I intersect all these sets going up to what, up to infinity, what do I get? So like that. So when I intersect these, 1 up to, okay, so when I continue, I intersect negative 1 over 2 there, half 2, then I intersect negative 1 over 3, 1 over 3. So I see that what element is common in what, in both. So I see when I go to this second part here, negative 1 and 1 is not in this part, and I go to this one here, negative half and half are not part of this part of this set. But as the interval even continues to become smaller and smaller and smaller, there is what, they are all approaching what, a common value, which is 0. So we see that the set here, or the intersection of this set, is just the set containing 0. So 0 is what is common in what, in all of them here. That is what is common. So we have this question. It's a 2024 exam question, and it says consider the family of intervals. So we have Jn such that n minus root of n comma n plus root of n, where n is a member of the natural numbers. So our indexing set is the natural numbers. Then we're told to find the union of the family of sets and also the intersection. So what we have here, we can see where these sets are taking us, or where they're going. So if we say J1 and I replace what, 1 where n is, I'll get that 1 minus root of 1, then okay, so then this is comma 1 plus root of 1, like that. And this then gives me, so this gives me here 1, I'll just have 1 in the root here, and this will just be 1 minus 1, which is 0. Then the next one, I get 1 plus 1, which is 2. So that's what I get in the first one. Then the second one, I replace 2 there, 2 minus root of 2 minus 2 plus root of 2, like that. So I'll get, when I evaluate this, I'll get 0.586 comma 3.414, like that. Then when I go 3, I'll get 3 there, root of 3 comma 3 plus root of 3 there. Then what I'll get is 1.268, like that. Then 4.732, like that. Then I have the fourth one. I can go up to the fourth one. Then the fourth one will just give me 4 root of 4, then I have 4 plus root of 4, like that. Then this is just going to be equal to 2 comma 6, like that. So now from here I see that as these sets are moving, this is shifting. So I have 0 comma 2, like that. So then it shifts. So when I look at in this interval that follows, 0 is not part of this here, but yeah, so it's shifting. So if we're trying to what, it's shifting towards the right hand side. All the intervals are shifting towards the right hand side. So now when let's answer this one. The first one says the union. So what will be the union? So the union meaning everything intersecting everything. So I see that my starting point is what, is 0, and this continues to shift. So the number is changing towards the what, towards the right interval. Even the left one is changing, but we see that our starting point is 0, and this is going up to what, up to infinity. So when we unite all those sets, we just have the union where n is equal to 1 of jn is going to be equal to 0 comma infinity, because they're going up to what, up to infinity. So that will be our union. Now what will be our intersection? So these sets continue to shift as you go towards the right, and we can observe that there is no common versus here. There will be no common element where these sets intersect, because it keeps on shifting towards the right. So this here will just give us the empty set, just be equal to the empty set. So that's how you work around this question. Okay, so another important concept that we must understand is De Morgan's law of the set of these arbitrary families. So now we have that we were dealing with De Morgan's law, where we just have two sets. We are dealing with A intersect y complement, then that being equal to x complement union y complement, like that. But then this is applicable even to a number of sets that we might not know. There can be hundreds of sets, there can be thousands of sets, it can be going up to infinity. We don't know like how many sets we can apply to this. So we can write this even in a general form using the arbitrary families of sets. So how do we do that? So the theorem is, let's say we have a set. So this being the arbitrary word family of sets, like that. Okay, so if we have this, and then where I is the what, is the indexing set. So where I is the indexing set, then we have that it's going to hold that the union of all these arbitrary families of sets starting from I, a member of the indexing set, like this, complement is going to be equal to the intersection of I, a member of the indexing set, then here the arbitrary family of sets complement, like that. So this is going to hold. Now how do we prove this? So we have to prove that this is going to hold. So in order to prove this, we say, so in order to prove this, the union of I, a member of I, like this, AI complement must be a subset of a, like that, the intersection of the complement of the arbitrary family of sets, and also vice versa. It must be what? It must be true that this also must be a subset of this other set. It must hold. That's when these two can be what? Can be equal. So now let's say, suppose, so our proof will go something like this. Um, suppose that we have an element x being a member of this complement of the union. So like this, IA complement. So suppose it's a member of that. Then what this means, it means that x is not a member of the union of these arbitrary families of sets. So it's not a member, x is not a member of I, it's not a member of A, like this, I, where I is a member of the indexing set. It's not a member of that. So this also means which for all. Okay, so this means, or this implies, this means that x is also not a member of AI for all I a member of the indexing set. So since it's not in the union, meaning it does not fall also in that what, in the arbitrary family of sets for all I a member of for all I a member of the indexing set. So this then means that x should be a member of a I complement, because it's not, does not sit in the arbitrary set, so it must sit in the complement of the arbitrary set. So if it's like that, so if it's like that, we'll have that x is then going to be a member of the intersection. Okay, so I didn't finish this statement here. So the statement here, x must be a member of the complement of this arbitrary family of sets for all I a member of the indexing set, so that x is a member of the intersection of the complements. So intersection of the complement of these arbitrary sets for I a member of the indexing set. So this then shows, us that the union, so the complement union, okay, like this, complement is just a subset of the intersection of this, like that. So this shows us that this is a what, is a subset of that. So we've shown the first way. Now let's show that the opposite or vice versa is true, that the intersection of the complement is the subset of the union of the complement there. So we can label this to say part 1 of our proof. Okay, now conversely, here you say conversely, suppose we have that x is a member of the intersection. So we're starting from the intersection this side for i's, like that, complement. So if it's a member of that, then thus x must belong to AI complement, like that, for all I a member of the indexing set. So if it's like this, then it means that x is not a member of AI, since it's in the complement. So it's not a member of AI for all I a member of the indexing set. So for all I a member of the indexing set. So if it's not there, meaning that this also, it follows that x is not in the union. So if it's not in this arbitrary set, meaning it can't be in the union of these arbitrary sets. So of those arbitrary sets, it's not in there, it's not contained in there. But if it's not in the union, it implies it's not in the union, it implies this must sit in the complement of what? Of the union. So meaning X is a member of what? The union of this complement of the union of these sets, like that. So it's a member of that. So hence now from here we see that the intersection of the complement of these arbitrary sets is just a subset of the union. The union, like that, the complement of the union of these arbitrary family of sets. And this here we can label what? 2. So now combining the two, so when we say combining what we found at first, 1 and 2, we will have that they are subsets of each other, so in both ways. And when sets are subsets of each other, meaning the other way around, vice versa, like a set is a subset, is contained in the other set, and that other set is contained in the other set, meaning these sets are going to be equal. So combining these two parts of the proof then shows us that indeed the union of all these sets I complement is equal to the intersection I indexing set I complement. And this is the end of our proof and this video.